Our next presentation by Clifford Schneider and Christine Fiori is on road construction technology in the High Cordillera. Christine Fiori is the Associate Director of the Myers-Lawson School of Construction at Virginia Tech. She received her PhD in civil engineering with a concentration in geotechnical engineering from Drexel University in 1997. Her interest in ancient construction led to a National Science Foundation grant to explore the construction techniques of the Inka, specifically the Inka Road throughout Peru. Fiori leads the construction, engineering, and management program and also facilitates the service learning programs for the Myers-Lawson School of Construction. She has led diverse groups of student teams to Vietnam, Kenya, Belize, Haiti, Guatemala to complete construction projects and community engagement programs. Currently, her work is focused in Haiti and Belize. Cliff Schexnayder, Choctaw, is Emeritus Eminent Scholar at the Del E. W. Webb School of Construction, Arizona State University. He holds civil engineering bachelor's degree and master's degrees from Georgia Institute of Technology and a PhD from Purdue University. Before entering academia, he worked with major heavy highway construction contractors as field engineer, estimator, and corporate chief engineer. In South America, he has taught construction engineering at the Universidad de Piura and Ricardo Palma Universidad in Peru. Schneider is a member of the National Academy of Construction, the Academia Panamericana de Ingeniería, and is a distinguished member of the American Society of Civil Engineers, ASCE. He served as chairman of the ASCE's Construction Division and Transportation Research Board's Construction Section. Clifford.
Thank you. Thank you.
Christine.
Ah, there you go. Oh, word. They told me I got to stand here because they're filming this, and my wife's in Philly watching it. So, I'm just excited. Christine's the one that did all the paperwork and got the money out of the NSF for us. I'm the gringo in the middle. Gerardo Chang is a professor of civil engineering at the Universidad de Piura. He was with us all 3 years as we went through. We went down there to dedicate with Ken Wright and Ruth Wright. Machu Picchu is an international civil engineering landmark. Romero Matos back here said, hey, I want to do this exhibit, and Christine went to NSF and got the money so we could go take a look at it. I got to stay here. Manuel was at Texas El Paso. This was in 10. He ran the underground of the radar, the ground penetrating radar for us. We had our llama driver who brought the llamas and took care of us and packed all our stuff. Gerardo is up there in the back with the dark glasses. We had to have somebody that spoke Quechua. Here's Christine. Megan's son walked the entire Inka Road in the highlands from Quito to Santiago, Chile. And so when we wanted to look at a bridge, or we wanted to look at pavement, or we wanted to look at a wall, we said, Megan, where do we go? And she took us there. She's got this trapdoor mind, and she could tell us where to go. I can't tell you how much help she's been to us on this project. Ed Jaselkis at North Carolina State University. The Smithsonian provided us with a link, and we would broadcast every day from the road back here and show the people what we were doing, where we were in the landscape, and everything else. So we had a burrow with this 8-foot satellite dish. We had another burrow with a generator, and another burrow with fuel for our generator. I'm the gringo here. We took a linguist from, at the time, she was doing her PhD at Berkeley, to help us with the language, because we wanted to know the stories for the different places. We did the first year because we said we better go try this out, see if we can do this. The grant was to also let undergraduate students have a research experience. So the second year we took students from the United States, Argentina, Chile, and Peru. We even took a high school student from Chile. I gave a talk. I was down there after the Mao earthquake. I gave a talk to high school students for the embassy. And at the end, this high school young man came up and said, I want to go with you. And so we were able to work that out. I can't pick him out. Oh, right there. Right here. We had a few dollars left over. So the last year, we decided to go try some of the road that other people had already walked and written about to confirm what they were telling us. We've seen this map. Maybe you don't understand this, though. If you draw a line from Santiago, Chile, horizontal now, Buenos Aires, Argentina, you are at the bottom of South America. You are at the very bottom of South America. Excuse me, Africa. Wrong country. South America is much longer, much further south to Antarctica. So that road in the highlands is over 3,000 miles. Cesar came with the conquistadors. He wrote about it. We've talked about it, some of the other speakers. You know, they came from Spain. They had seen the Roman roads in Spain. They had seen the bridges. John talked about the difference in bridges. You know, this is 200 conquistadors against thousands of Indians. They're looking for the gold. I mean, these are crazy hombres. Yet when they saw that bridge that John was talking about, that suspension bridge, they literally got down on their hands and knees. These crazy guys were scared. How did they do it? How did they do it? It is an amazing thing. They did it by paying attention to nature. This is Qhapaq. These are the terraces where they grow food. To be able to have that manpower that we were talking about, the Quipu and building in Bolivia a minute ago, you had to produce enough extra food to feed people that were not growing food. If you didn't do that, you couldn't do all these civil works things. You couldn't build that city that we talked about this morning. They built those terraces for agriculture. That gave them the knowledge, though, to build. It gave them the knowledge about controlling water. Their civil engineering, as far as infrastructure, came from knowledge gained from doing agriculture. The population today along that Andes is just now coming back to the population it was when the Inca was there, because they produced enough food to support that size population. This is the market on Sunday in La Union. I want you to look at this. They produce as many fruits, vegetable species of food as Europe and Asia combined. They knew agriculture. They learned it by paying attention to their environment. I'm wearing the hat for a reason. You see the little band? Probably some 5 or 6-year-old young lady did that band. When they got to be about 10, they do bands that are about like this. And when they're grown women, they're like this. All of that knowledge to do that pattern is this onboard computer. They had the Quipu to do this counting thing. But the other knowledge about nature and working with nature and the forces of nature came from what they stored up in this onboard computer. I'm going to turn this over to Chris to do the fun part now.
Thank you, Cliff. Well, what I'm going to do today is to take you along the journey that we did, walking the road, and give you a little bit of the fundamentals of the engineering experiences that we had, and also kind of treat you to some of the things that we learned as we were walking along the road. Now, as Cliff said, we were a bunch of gringo engineers coming down there to take a look at what was going on. But without the help of our archaeologists, our historians, and our linguists, we would have missed so much. Specifically, when we began this project, we saw these walls, and we noticed that when we walked through areas where there were crops, the road got narrower, and there were walls on the side. And as we began to look at the history and understanding, this is an agricultural area, okay, that we were walking through. Agricultural land is very precious, so naturally the road narrowed. The Inka understood how important cropland was to the production of food throughout the empire. And so the road narrowed, okay, and these walls were built. And these walls were meant to protect the crops from travelers, okay, and llamas, okay, from entering into those fields and potentially eating those crops. So the way that the road moved through the landscape all depended upon where you were, at what elevation, and what the surrounding land was used for. And that was something that we would have completely missed, okay, if we didn't have our historians educating us about the importance of these agricultural lands. Now, depending upon the area you were in, these particular walls would be built out of either stone, okay, and in this section right here, this is north of Tambillo, where we started our trek. And it's all natural stones, or all stones from the local area, but it could also be built with adobe or another type of mud wall system, depended upon where you were. Now, we've heard throughout all the presentations today that the Inka built in harmony with nature, and that they also built in some of the most challenging environments on the planet. Okay, these include a lot of water. And these photographs right here, most people say, oh, well, it must have been of an El Nino year. No, it was just a good strong rain. This happened back in January of 2010. This picture is at the base of Machu Picchu in the town of Aguas Calientes. This rainfall actually washed out the only railroad access to the town of Aguas Calientes, and people were trapped. It actually increased the water flow in the Urubamba River by 3 times. And yet, the road around Machu Picchu and Machu Picchu were just fine. Our modern structures are what failed. So they had to deal with a lot of water, no doubt. Another thing is the environment can change very rapidly at high altitudes. Okay, we experienced this firsthand 2 summers ago as we were trekking along trying to get back to our vehicle while we were measuring the roads. And we saw a storm kind of coming in on the horizon. It was probably 60, 70 degrees out as we were walking along that day. Sun was bright. Within about a half an hour, this hailstorm came out of nowhere, okay, and dumped hail on us for probably about 20, 30 minutes while we raced to the car. So the atmosphere that you're building in can change very rapidly. So you're dealing with a lot of rain. You potentially have very rapidly changing temperatures in the area. And additionally, we have a lot of rain, but we also are going to be building in areas that are deserts, okay? And the road in the area where there were actual deserts, that particular stretches of road was just kind of moving stones to the side and actually defining where the road was. So there were different engineering challenges in every location, whether it be going through croplands, dealing with water, or dealing in a very arid climate with lots of different changes in temperature. So we've got all those environmental factors. Now let's add to it, oh, by the way, we have earthquakes. Okay, we have earthquakes in this area, and the South American West Coast, okay, is on the circum-Pacific seismic belt, okay, where more than 2/3 of the world's largest magnitude earthquakes occur. Okay, so now we've got all this weather that we have to deal with. Oh, we also have earthquakes. And what you see in this picture here is from the earthquake that happened in Peru in 2007. And what happened to the infrastructure there, in some places, the road was completely demolished, making vehicle travel very difficult to get to. Yet the Inka structures still remained. But our modern structures had failed. Again, another concern that the Inka had to deal with. One of the things that we noticed most readily, and you've heard throughout the presentations today, was the power of water and understanding and working in harmony with nature. And the energy of nature is what the Inka really understood. We're going to start with water. And it's one of our favorite topics when we began to look at this particular structure. And with the energy of water, okay, it can be very damaging and very destructive. And in an area where you have about 80 inches of rainfall a year, okay, or areas where you don't have a lot of rainfall, depending upon where you're building, that dictated the type and the size and the shape and the surface of the road. So in this picture right here, this is coming through an area south of Baños where we worked our last year. And what you see is the road itself is fairly wide and it's covered with grass. Okay, in this particular area, because of the flatness of the road and the area was not as steep, the road was simply a grass structure with some retention walls and contention walls to support the road. Okay, so in this particular instance, there wasn't a whole lot of engineering that needed to be done, okay, because of the way the water flowed over the road. Now, what we saw also as we moved across this landscape was that if the terrain got pretty challenging and very vertical, the Inka would build steps. Okay? But also as we walked along, confirming some of the things that were previously recorded by Hyslop, we also found these random collections of single, double, or triple steps in an area. And we began to look around us and look at the landscape and began to see that if the Inka were going to build something, okay, they were very focused on the amount of energy that was required to do that. And if they were going to actually build these steps, there had to be a pretty good reason to do that, to expend that type of human energy to build that particular type of step. And what we determined is that these particular steps were used to help slow down water that could potentially be flowing over the road surface and potentially erode the surface. What these particular steps did is they act as energy dissipators, slowed down the water to prevent erosion on the road. So they weren't necessarily there just as something for us to step over in certain areas. So we found that they were there to dissipate energy. Okay? In areas where the road was steep, we saw these. These are some examples, okay, of where we actually saw these particular types and series of steps. Okay, these are a set of single steps, and this is on a mountain pass heading up out of Tambillo into, working our way up to, there's a mountain pass around the corner here at about 15,000 feet. And in coming up this particular area, we found this series of steps. And what these were designed to do is that as water would come down, it would slow down the water. Additionally, some of the water could be trapped along these steps and shunted to either side of the road. What you see in this picture is our guide, Basilio, a native Quechuan who helped us move along throughout our entire expedition, and Gerardo Chang. And what they have there is a ground-penetrating radar system. So we didn't really travel light. Our poor llamas had lots of equipment strapped to them, and in addition to our satellite equipment. But what we were doing was actually looking at the foundation system of the road. And we were also curious to know what was going on behind the retaining wall systems, because we had read and studied the work of other individuals relating to retaining wall structures, specifically the work of Ken and Ruth Wright on Machu Picchu, and looking at those terrace systems. We were really curious to find out what was underneath these roads. So we had that system there, but this slide right here is just to show you that as we move up this mountain, okay, where you're going to have potentially a lot of rainwater coming down, or also snow melt. Okay, we're up at 15,000 feet. It gets a little cold up there. And what you see here is just the examples of those steps. Now, as you continued further up the mountain, okay, the actual situation that we encountered on those higher elevations, and these areas weren't suitable for agricultural purposes. Okay, these are grassland areas where typically only llamas would feed. But in these areas, to help prevent the erosion of the actual road, they would pave the road with locally available stones. Additionally, we saw this type of paving when the road became a little steeper at a grade of about 15 degrees, okay, or in areas where agriculture was not feasible at higher elevations, okay, again, to prevent the erosion of the surface of the road. Now, you may look at this pavement, and I realize this is 500 years old, without a whole lot of maintenance. It may look like some of the streets in DC come springtime with a lot of potholes, but this particular type of road and the paved surface with these rocks was there primarily for energy dissipation. It was not structural. Okay? Because when you think about what was actually traveling on these roads, so modern engineers, we look at what's our design vehicle, what's going to be rolling over this road, what type of durability do we need? Well, this road was built for men walking, okay, wearing sandals, okay, made out of the sisal grass. Okay, so walking over these types of stones, they would not damage the stones at all. Okay, there were no carts or things like that being moved across the road because the wheel isn't very useful in a vertical environment. And so you didn't see any of this until the Spanish came. So these particular road systems and the paving was only to prevent erosion. It was not structural. So now we've got it designed for men walking. We also have to think about who was carrying all the load, and that was the llamas. And this picture right here, if you look at the llama, okay, it's a camelid, and it has undulated feet, okay, or it's bump-footed. And so the motion of a llama walking over the surface, okay, is not going to tear up that road either. So the way the road was designed, again, we were expecting the paving stones to be structural, and we had all these grand ideas of what we were going to find. And when we actually looked at what was the purpose of the road, and what was it designed for? Okay, designed for these llama caravans, okay, and some of the conquistadors wrote about this, that they had llama caravans of the thousands or tens of thousands of llamas moving over this roadway. Their feet would not tear this road up. We only had 8 llamas moving across the area when we were out there, but they didn't tear up the road either. So what we did with our ground penetrating radar was we went into different areas that had been paved or looked in different locations where we thought there would have been some additional paving. And it was really the results of our ground penetrating radar research that led us to the conclusion that the roads were only paved where there was the possibility of high water energy running over the surface. Okay, additionally, the roads were paved in areas where there wasn't potential use for agriculture. And so we saw this, and with our ground penetrating radar analysis, what we found is the typical depth of these paving stones was about 20 centimeters or 8 inches. Okay, so not incredibly deep like we were potentially expecting. And again, it goes back to what was the road designed to do. And so we used the ground penetrating radar system hoping to find more evidence of some structural support, but what it really led us to was the conclusion that I've already stated, that these were designed to help control and prevent erosion. So water, very important to the Inkas. Other ways that they controlled water, and we came across examples of every single one of these particular types of water control devices. You had a combination of different types of systems that would move water either across the road, under the road, or around the road. Raised stone drains were very common. Open stone line culverts crossed the road. And then capped culverts, okay, and we as engineers, when we were first going out to this particular area, they were telling us they were taking us to a bridge. We were very, very excited, and I'll show you the picture of the bridge. We were expecting a very nice, long bridge, and what we got was 2 culverts. And we were trying to explain to the people that were guiding us, well, they're just culverts. Well, to engineers that means something, but to the rest of the world, they look like a bridge. But really what they are is just capped areas that you were able to cross along with the road. Additionally, there were also culverts that were built underneath the road, specifically in areas where the road was built between 2 retaining walls, is what we found. Here's an example of a raised stone drain. Water would come down, okay, hit this stone drain and be shunted to either side. So the drain was built right across the road of the direction of travel. Again, you're not worried about the wheel. Okay, you're walking and you have llamas. So these particular raised stone drains didn't cause any problems there. Additionally, where we found most of these raised stone drains were in areas where you didn't see any paving. Okay, we generally found these in grassland areas. And in our 3rd year of research, we actually confirmed that in several different places along the road. The open channel, or the open stone line culverts, went directly across the road also. And how they worked was that water would be moved from the high side of the road to the low side of the road, allowing it to move directly across the road without causing any erosion. And what you see in this picture, okay, yes, if you were running a wheeled vehicle over this, it would be a little bit of an irritant of hitting almost a control joint as you move across that ditch. But in the era of the Inka, you didn't have to worry about the wheel. People were walking, llamas would walk across these. In this particular picture, you can see that in the interior of this open stone channel, what you see is that it's been overgrown, and that is potentially causing some degradation to the road. Okay, so imagine not maintaining something for 500 years, but it still looks this good. Okay. This is a bridge structure that we investigated in year 3. And we were looking at this particular bridge structure to see different aspects of culverts, okay, and how they actually were able to allow the water to flow through these systems, okay, without causing a whole lot of erosion on either bank, okay, or at the bottom of these culvert systems. This particular bridge, okay, was up at about 12,000 feet, and each one of these stone-capped culverts or bridge sections, there were 9 of them. And what we found consistently within most of our culvert sections, and we really measured these in very much detail, was that as the water came through from the upstream side to the downstream side, what you saw was in this culvert there were steps. Okay? And what these steps do, okay, is they slow down the water. They help dissipate energy and reduce the erosion potential that could occur on the other side of that actual culvert. Okay? So it was, we looked at this structure, we saw this structure, we saw several other structures with that stepping down effect, again, dissipating the energy of water. They understood how much erosion water could actually cause. Now, in addition to the culverts across the road, having culverts along the road, what we also see, okay, is these stone culverts used in conjunction with an open line culvert. Okay, so they weren't just all, these particular water structures and water control structures could be used in conjunction with one another. Okay, this was the bridge that I was telling you about earlier. We were expecting a nice big bridge, but we found these 2 culverts, but it was still fantastic to investigate because again, we found that the water was stepped down to dissipate some of that water energy, allowing for a more durable structure. Additionally, in this picture, what you also see is the open stone line culvert, which shed water on either side of the bridge, or of the culvert section. What was interesting about this particular area is that there wasn't a stream here. What was actually causing the water to flow was maybe a little hard to see, but this black rock right here is a volcanic dike, okay, that has cut off the water flow from that side of the mountain. So the water would come down right along that particular area, needed to move across the road. Okay, and so they built these culverts and the open stone line channel, okay, so that the water would actually move. In addition to culverts, channels across the road, they also looked at combining side ditches, okay, on the uphill side or the uphill side of the actual road, the high side, collecting that water and moving it down across the roadway where it would not damage and cause any type of erosion. Now, the Inka controlled their slopes, okay, so they controlled water very well, and another way they actually controlled water, okay, and also made sure that the road did not wash away was through retaining wall structures. And the retaining wall structure and technology that was actually used was adaptations from the lessons that they learned by building their agricultural terraces. So everything goes back to the control of water and what they learned from the tremendous amount of research and energy that they spent building those agricultural terraces. Now, these retaining wall structures, as you can see in this picture, they do not have any cement in between them, in between the rocks, and what it allowed for is water to flow down and through the rocks, not allowing for any hydrostatic pressure to build up behind the walls, potentially causing some failure. So water could move directly through these walls. Now, unlike the agricultural terraces, we ran ground penetrating radar tests across the back of these walls, hoping to find what we would see on the agricultural terraces of that inverted filter. But what we found was there was no special type of filter behind these walls. We concluded that it was just the open structure and having no cement or any type of bonding material within the wall structures that allowed for the water to move. In addition to the retaining walls, and the retaining walls were going to hold up the wall okay, or hold up the soil on one side of the potential road and allowing the road to remain open. Another type of wall that we encountered were called contention walls. And these contention walls were on the lower side of the road. And in this particular picture right here, what we're showing is that they're about 60 centimeters wide, and in between, there's soil. And what that does is the walls have a slight batter to them. With the soil in between, it gives the wall additional seismic capabilities. These particular walls were used to hold up the road. Okay? And so it was very important that the road remained stable in any type of seismic event. And we believe this is one of the ways that they did it with these contention walls, so that you had almost two wall systems sandwiched together. Now, they also understood the area that they were building in. They understood the type of soil that was available within the area, and we found specific examples of this in this particular area that was low-lying, that water could run through, but not at a very high rate. What we saw was this causeway that came down from the mountain and crossed this very tiny little stream here. And we noticed that there was several different excavations, and we looked around the area to see the soil type. And they understood that clay soil would be durable in this particular situation, okay? And they used the clay material. And this is what we were surmising. And then Cliff went down to the river. We dug up some of the clay, some of the soil material that was actually on the road to see what it was, and lo and behold, it was clay. So they utilized the natural materials to build this particular causeway section. The other thing, when we talk about energy, is the Inka understood not only the energy of water, but also the energy of humans and animals. Okay? And when you look at this particular picture that was taken south of San Cristobal de Tambo, when you look in profile here, you see a very uniform grade. Okay, the Inka liked to build things in straight lines, okay, is what we encountered, because they understood that additional travel distances was going to require a lot of energy from the traveler, as well as the llamas that were moving along with the caravans. And so what they did, the way that they actually achieved this, was what we would call directional straightness. And it's absolutely amazing how they did this in such a challenging physical environment. And when you look at the road, which we would often do as we were hiking along, we'd turn back to see where we had come from every day, to see how far we had walked. And we looked back at the road, and we saw in profile here a straight line at a constant and uniform grade. Now, if you were here earlier for the rights presentation, you saw the consistent grades that were developed for most of their trails and most of their roads. And so the challenge of doing that is just absolutely amazing in this type of vertical environment. Now, when they had to maintain that directional straightness, sometimes they did have to cut through the rock, okay, and excavate the rock. And how they did that is we believe that they used the same technology that the Romans did. And that was to build a fire, or build a fierce fire next to the rock, and then throw water on it to crack the rock, and they began to work that particular excavation, okay, in these areas. But this was to maintain that directional straightness, minimizing the amount of energy that was required by the traveler and the llama, okay, to move through this particular area. When they had to, okay, they would build steps, okay, to also continue to achieve this directional straightness. And it also provided a way to move through this vertical environment in an easier fashion. Now, we saw many examples of steps, okay, and the steps tended to be narrow, okay, but if they had to, okay, in these physically challenging environments, they would build these steps or switchbacks to, again, minimize the amount of energy that it would take for the traveler. Now, this also required a lot of energy to be expended in the building of these particular structures, okay, but the ultimate goal was to minimize the energy expended by the traveler. Now, these steps, okay, didn't cause any problems, okay, in the Inka environment, primarily because with this verticality that you're dealing with, again, the wheel was not a standard type of vehicle that was utilized. Your standard vehicle was right here. Okay, your llamas. And the llamas have no problem moving up and down stairs. Okay, they're not afraid of them. They'll move up and down them very easily, and they won't damage them. So this particular road that we walked in many different segments, and we saw consistently, over and over again, an excellent understanding of the energy required to build, the energy required to travel, as well as the energy that had to be dissipated with the water to ensure that that road would last for the centuries. As we wandered along, okay, we stayed in many different villages, okay, and every evening we were treated to the abundant different types of material or types of food that the Incas had. And in this particular photo, this is of our team the first year. It was a very cold night in Tauli. And of course, we were eating our favorite meal, potato soup. And we had lots of potato soup on this trip. But the idea that we set out to find was to determine how and why this road lasted so long. We had many different theories when we started walking the road, and we missed a lot of things because we were easily distracted. Unlike the Inca, who really observed and looked holistically when they built. So if there's one thing that we took away from this in terms of how we as modern engineers could begin to utilize some of these sustainable technologies that the Inca actually employed throughout their empire, it was to really pay attention and to design in a holistic manner that considered the earth as something sacred and something to be worked in harmony with versus to be dominated. So we really learned a lot, and we're hoping to learn even more as we continue this research. And before I go, I need to acknowledge several people that worked on this project. The National Science Foundation gave us funding. The Smithsonian gave us several hours of support and supported our broadcasts from the road. Gerardo, Chang, and the University of Piura, our partners in Peru, were absolutely phenomenal, okay, as well as Ed Jaselskis, who gave us the idea that, hey, not everybody can tromp around at 14,000 feet, but we're pretty sure people would want to see this. So let's bring it to them live. And we were like, okay, we'll see how we can do that. And we did it through the support of all these individuals. Additionally, Cliff mentioned Megan's son, who helped us quite a bit because she had walked the road and knew the road. We also had excellent guide services, as well as the support of our archaeologist, Alexei Vranich, helped us out tremendously throughout this particular project. But overall, it's been a tremendous journey, and I was very excited to share it with you. Thank you.